Hello everyone. So today we will be discussing the difference of quasi-static and dynamic deformation from the atomic perspective. So although we will be explaining our wave propagation problem with a continuum approach in the rest of the courses, but it is important to understand how the deformation happens in atomic level. So now we will see both the quasi-static and dynamic deformation from the atomic structure perspective. So this is an array of atom. So we can imagine as a long bar. So we are having 4 sections. Let's write as section A, section B, section C and section D. So this is a bar in 2 dimension we are seeing. So we will have 2 forces here, the same forces on the left side and right side, that is compressive in nature. So we need to be careful here. So although we are showing the deformation of the body with some atomic movement here, this may not represent the exact atomic movements, because we will have crystallographic constraints during these atomic movements. Applying the forces, applying a force in a solid body is a dynamic process by definition. By definition is a dynamic process. It's by definition. Why? Because the force is being applied, and the material will deform continuously. So that's why it is a by definition dynamic process. But if the rate of change of applied force, if the rate of change of applied force is low, then we can consider the process as a sequence of steps in which the body is in static equilibrium. Steps, the body is in static equilibrium. Static equilibrium. We will demonstrate the 2 processes, both quasi-static and dynamic processes, with atomic movement now. So this animation is not perfect, so we will see how the atoms will deform. It is just to give you an rough idea about the atomic movements. Sorry, this actually the ABCD is now going away from the section, but anyways we can have write it again. So this is the so this is, we'll see this again, we'll see this once again. So you are applying the forces from both the end, and now what is happening here is the interatomic distance is reducing, that is reducing uniformly in the entire bar A, B or C and D in all the sections. If we can see that the interatomic distances are same, and all the sections A, B, C, D, section A, B, C, D experiences identical stresses. Identical stresses at every stage of deformation, and this will, as we discuss, at every stage of this deformation can be considered as a static equilibrium we can consider every step as a static equilibrium, and we can solve this problem using mechanics of materials approach. Which is cannot be possible using for dynamic deformation, and also the inertia forces are neglected here. Inertia forces are neglected in case of quasi-static deformation. So now we will see the dynamic deformation case. Here we will be taking the same bar in 2 dimension, and we will give the same kind of loading, that is in compression from both the ends. So we have, again we are having 4 sections just to explain the problem, and here we have rapid loading, or it can be rapidly changing loading. It can be rapid loading or rapidly changing loading. So if it is rapid loading, the internal stresses are not instantaneously transmitted throughout the body. So these stresses from these point of disturbances, it doesn't transfer instantaneously. So this is our source of disturbance, we can call where the point of application of the force, source of disturbance. Source of disturbance. So from the source of disturbance, the disturbance should go this way, and similarly from the other side, right hand side, the disturbances will come this way. And as we know, our loading is a rapid loading or rapidly changing loading. The disturbances are not instantaneously transmitted to the other part of the body, and we cannot assume static equilibrium like our quasi-static case. No static equilibrium. No not applied here. Okay. So static equilibrium not applied here. So in the dynamic case, in the figure, the interatomic distances will be reduced when you run the animation. So the interatomic distances will be reduced, and a group of atom we can see with the red atoms will be compressed at first, and this disturbances will propagate. So now in this case, as we are exerting the load from both the sides, we can see the disturbances are moving both from left and right towards the center. So now if you see in any intermediate position, let's say in this position we have the section A here, section B here, C here and D here. So in that position, so what will happen is section A and D, section A and D will experience the stress, but at that time section B and C will not experience the stress. But after some time, so we can see section B and C will now experience the stress. Section B and C will experience the stress. Now A and B, the stresses will be reduced or it may vanish. So whatever we are discussing, this propagation of the disturbance is nothing but wave propagation. Wave propagation. This is called wave propagation, and this is actually elastic wave propagation. As the deformation is elastic, later we will get some other types of wave like plastic waves. So this is elastic wave propagation, and in this case the atoms are experiencing considerable acceleration. And these acceleration will give the inertia force, which is a fictitious force, and that is equal to negative of mass into acceleration, that acts in opposite direction. So in the quasi-static case we ignore the acceleration and we can neglect the inertia force, but in this case we cannot ignore the inertia force or inertia effect. Let us now think about this. So I am running the this animation again. So we were deforming from both left side and right hand side. So what is happening here is this group of atoms are moving towards each other. So now how can you determine that how many rows of vertical rows of atom, that means here in this case we have only 2 rows, so how many rows of atoms will be grouped together, and these atoms will move towards the other side of the body. So that is actually the group of compressed atoms gives us the wavelength. So that is related to wavelength of this elastic wave, and these wavelength can be changed, we can change the wavelength by changing the initial deformation. That means here in this case the whatever displacement we are giving here, this is the first step now, and this is the second step. Again, this is the first step when we are just having the force, and then in the second step we are having the deformation. I am running it again and again. So that deformation, or actually the displacement, that displacement will decide what will be the wavelength. So higher that initial displacement, higher will be the wavelength. And later in case of split Hopkinson pressure bar, that split Hopkinson pressure bar is an experiment we discussed earlier. So in case of split Hopkinson pressure bar, we will see that wavelength, this wavelength is related to length of the striker bar. So basically we will see that is probably twice the length of the striker bar. Wavelength of the elastic wave in a split Hopkinson pressure bar experiment is twice the length of the striker bar. Striker bar is the projectile. Suppose in this case we have a bar like this on the right hand side. So this is the bar which is hitting the material, and so what is the length of the striker bar, that is will decide the initial displacement, and that will decide the wavelength. We can write lambda, sorry, this is not exactly the wavelength. The wavelength is not exactly the dimension of the compressed region of atoms, it is more than that. It can be probably twice of that width of that compressed region of atoms. So that's what we know about, we discussed about dynamic deformation. So we'll go to the next part of it. This is, we will see the elastic wave, we will discuss about the elastic wave with an atomic perspective here. So what we discussed in the previous slides is we were assuming a very idealized atomic structure without considering any a crystallographic constraint. In this case also, whatever we have shown in this slide, so this is also kind of an idealized linear array of atoms that may not be the exact case in reality, but here whatever we are seeing is this solid circles. The solid circles are the equilibrium positions of the atom, and we know these atoms actually oscillates, these atoms will oscillate at a very high frequency, very high frequency. So and these oscillations can be broken down into three directions, that's what we are doing, x1, x2 and x3. It can be broken down into three directions. That frequency of oscillation, atomic oscillation is very high, is 10 to the power 13 per second, or we can write hertz. So in a second it will oscillate 10 to the power 13 times. So and we have broken down this into x1, x2, x3 direction, and we will now see how we can determine the elastic wave velocity, an approximate determination of elastic wave velocity from these atomic perspective. So we are giving a force from left side, we don't have a force from right side this time, so we have a force from this side. So if we can accelerate the atoms to a certain velocity, the atom, this atom, the first atom on the left side will transfer its momentum to the second atom, and similarly the second atom after some time will transfer its momentum to the third atom, and similarly it will go on to the subsequent atoms. So basically this the wave speed, how these disturbances will propagate throughout this material depend on three things. The first one is mass of these atoms, and second is interatomic distance, and third is interatomic force, whatever attractive or repulsive force in between these atoms. So this is that factors influence, these factors influence wave speed. So these dark circles are, these are equilibrium positions of atom, equilibrium position, and these are extreme positions. So I have got this some animation, and I modified it from the internet Wikimedia. So and then I modified it a little bit to just show you a rough idea, to give you a rough idea of the atomic oscillations. Let's assume that this circle is the original position of atom, and then it is oscillating right to left. So now these oscillation is not exactly independent of each other. That means one atom oscillation is not independent of the other oscillations of other atoms, and this collective excitation of the lattice is known as phonon. So the collective excitation of the entire lattice is called phonons, and the field of study is called lattice dynamics. We will not discuss these things, but just for your reference, you can probably, if you are interested, you can study about these. So now when we are exerting a force from, let's say, left side, we are giving some disturbances F. So what will happen is the first atom will transfer the disturbances to the second atom, and then second atom will transfer to the third atom. So it will go on. There are two approaches, by the way, to study these elastic wave velocity. The first one is the continuum approach. Continuum approach. Continuum approach. That is what we will be discussing in this course. So that means continuum means the mass is uniformly distributed, and we are not considering any discrete atoms or molecules. So we can use Newton's second law. To derive our wave equation, wave propagation equation. And the other one is, the second one is considering the atoms. We will not be discussing on this much, but we will be focus on continuum approach in rest of our course. So basically what we want to show you here is how we can determine an approximate value of wave velocity. So when the force is applied on the left side, as you can see, force is applied on the left side, the disturbances will not be transmitted to the other atoms instantly. It's not instantly. It will take time, very little time, but still it will need some time. So that time difference, what will be the time difference? So that is equal to the time difference, or time lag for transferring the disturbance from the atom 1 to the atom 2 is the time period of vibration. Of atomic oscillation. Okay, and we know the time period of vibration, as I told you, the frequency is 10 to the power 13 hertz. That means the time period is 10 to the power minus 13 second. Okay. So then how to calculate the velocity, wave velocity? So we need to know the interatomic distance. So interatomic distance we need to know, as we know that wave velocity v is equal to x, let's say interatomic distance is x, and then let's say time period is t. So interatomic distance, let's say for iron, is 3 angstrom. It's close to 3 angstrom, 3 to the power minus 10 meter, and divided by your time period, that is 3 to the power minus 13 second, 10 to the power minus 13 second, and this will give you a value 3 to the power 3000, actually 3000 meter per second. So if you see the elastic wave velocity, in iron is I think around 3500 meter per second. So which is close to this value. So our calculations, which is a very simplistic calculation, is actually giving us a very close estimation. This estimation is very close to what is found from experiments, that wave velocity in iron is 3500 meter per second. What we did here is we are discussing just how this disturbances, that is the force or the internal stresses, will transfer from one atom to other atom. So that is, it is taking a time of 10 to the power minus 13 second, which is the time period of atomic oscillation, and we know the interatomic distance. We are considering iron as our material, and that is giving us 3 to the power 3 into 10 to the power 3 meter per second wave velocity. So we will demonstrate this quasi-static and dynamic deformation with the help of a spring. So this will be our spring. We will demonstrate that in a while. So this will be our spring, and we will see that if we consider a quasi-static case, and if we try to give a tensile load, then what we will see that coils of the spring will be will have identical extension. But in the dynamic case, we will try to have a generate a wave, and that will give us that we'll get a wave which will be, let's say, compression here and compression and rarefaction. So that compression, this portion will propagate. Sorry, this is again removed. So this compression part will whatever we saw in the earlier slides with respect to from atomic perspective. So we'll see in a while with a spring that compression will propagate, and this is actually a longitudinal wave in a spring. Now we will see how a quasi-static deformation happens. If we stretch the spring very slowly, if we can see that the distance between these is uniformly elongated, and we can say that a static equilibrium exists in the entire spring. So now we will see how the dynamic deformation happens. We can see a wave propagation here, longitudinal wave propagation, and wave goes and reflects back from the other end. That's all for today. We will continue in next lecture.